In this next section, we're going to look at double angle, half angle, and product of sum formulas. Here we are going to consider some more identities that will allow us to evaluate trigonometric values of more angles. Okay, so you want to recall in the first few sections we talked about some of the nice angles, pi over 2, pi over 4, pi over 6, pi over 3, all of our quadrantal angles, and translated those to degrees. Now we're going to be able to look at some other angles, not only in the first quadrant, but in the other quadrants as well. These first formulas you do not need to memorize, but they are useful in obtaining later formulas. And these are the addition and subtraction formulas. So sine of s plus t, so if s and t are two different angles, then this is going to equal the sine of s cosine of t plus cosine of s sine of t. Cosine of s plus t is cosine of s cosine t minus sine of s sine of t. And tangent of s plus t is tangent of s plus tangent of t divided by 1 minus tangent of s tangent of t. So again, you don't need to memorize these, but you should reference them in your textbook or some other source and keep them for later use. For the subtraction properties of these formulas, we can use the even and odd properties to get, for example, s minus sine of s minus t or cosine of s minus t. So the first formulas we're going to look at are the double angle formulas. The first set of formulas you'll need to know both for this course and later in calculus are these double angle formulas. If x is an angle which is in standard position, then sine of 2x is going to be 2 sine of x cosine of x. Cosine of 2x has three different formulas depending on what values you know. Cosine of 2x could equal cosine squared x minus sine squared x. Be careful not to confuse that with your Pythagorean identity. Cosine of 2x could equal 1 minus 2 sine squared of x, or cosine of 2x could equal 2 cosine squared x minus 1. And then tangent of 2x is going to be 2 tangent of x minus divided by 1 minus tangent squared x. And now again with these properties we give you sine, cosine, and tangent. To find the other three trig functions you can use your reciprocal identities or your reciprocal identities. Again we give you the sine, cosine, and tangent. To get the other three trig functions you can use your reciprocal or Pythagorean identities to solve for cosecants, secants, and cotangents. These formulas can also be used to reduce powers on trig functions. And so if we're looking at sine squared of x equaling 1 minus cosine of 2x over 2, cosine of squared of x is going to be 1 plus cosine of 2x over 2, and tangent squared x is 1 minus cosine of 2x over 1 plus cosine of 2x. And so you'll notice that in these formulas, the function on the outside is of an angle x, whereas the function on the other side is of an angle 2x, and one side it's squared and the other side it's not. So it really is a power reduction formula. For the exam and later for the calculus class, you will definitely need to know these formulas. And again, the reason you need to know those formulas and not necessarily the power reducing is because you can derive the power reducing formulas from these. Once you have these formulas, you will be able to do other things like solve equations, find other angle values, and later in calculus take derivatives or integrate functions. So now let's look at some examples excuse me, of using our double angle formulas. So let's say we want to find sine of 2x, cosine of 2x, and tangent of 2x, given that cosine of x is equal to 4/5 and the cosecant of x is negative. So to do this, the first thing we need to do is set up our triangle and find the relationship between the side lengths. So we do this for many of our other problems as well. So here we're going to start with setting up our triangle. So notice I've put the triangle in the fourth quadrant, and that's again because our cosine is positive, but the cosecant is negative. And so the only place that's going to happen is in the fourth quadrant. Using the Pythagorean theorem, we can see that the other side of our triangle is going to be -3. And again, the negative the negative comes from the fact that it is in the fourth quadrant. So now we can find both sine and cosine of x, which is exactly what we need to find all of our double angle formulas. So here we can see, using the sine and cosine, sine of 2x is going to equal 2 sine x times cosine x, and so we can plug in our values and multiply to get negative 24 over 25. And again, that makes sense since x is in quadrant 4, so our sine is going to be negative. If we look at cosine of 2x, this is going to be 2 cosine squared x minus 1. Now again, there were 3 different formulas for cosine of 2x, and you can use any of the 3. In this case, we were given the information about cosine, so as much as we can use that and not the other ones we derived, the more accurate we're likely to be. So here, 2 times 4/5 squared minus 1 will give us 7 over 25. And then for tangent of 2x, here we can use the double angle formula, but we can also remember that tangent is sine over cosine. So since we have both of those values, negative 24/25 divided by 7/25 gives us a tangent of 2x equaling negative 24/7. In our next example, let's use our double angle formula to evaluate one of our trig functions, or compositions. So cosine of 2, tangent inverse of 12/5. Well, to do this, just like the ones we did before, we're going to start with that inside piece of the function and look at setting up the triangle. So looking at the inverse tangent of 12/5 equaling theta, so tangent of theta equals 12/5 gives us a right triangle with opposite over adjacent being 12 over 5, and then we can solve using the Pythagorean theorem to get the other side of 13. So now if we look at our function that we're trying to find, we can see that cosine of 2 theta is going to be cosine squared theta minus sine squared theta. And again, because we have the triangle relating the sides of theta, we can plug in those values. So cosine of theta is going to be 5 over 13, and sine of theta is going to be 12 over 13. So simplifying that expression, we see that cosine of 2 tangent inverse of 12/5 is going to be negative 119 over 169. In some cases, you may be asked to just simplify expressions using our double angle formula. And this is going to come in later when we start solving equations. We may have to use the formulas to get one side down to a single trig function. So in this case, we want to simplify the expression cosine squared of 5 theta minus sine squared of 5 theta. Now at first, it doesn't always seem apparent how to simplify that. But again, if we look at our double angle formulas, I'm basically looking at a cosine squared of something minus sine squared of something, which, as we can go back to our formulas, we can see that this is going to be cosine of 2 times that value. And then simplifying that expression, that's just cosine of 10 theta. Now without knowing what theta is, that doesn't necessarily look simplified, but if I know what theta is, I can then evaluate, because I'm just looking at cosine of an angle. Okay. In another example, let's simplify the expression 2 tangent of 7 degrees divided by 1 minus tangent squared of 7 degrees. So this again is our double angle formula for tangent. And so here again, because our angle in the expression is 7 degrees, we can go ahead and multiply that by 2. And so again, for simplifying the expression, we get tangent of 14 degrees. Again, if we wanted to evaluate, now we could do that because we're back to just a tangent of an angle. The second set of formulas we're going to look at are half angle formulas. Here, if x is an angle in standard position, then sine of x over 2 is going to be plus or minus the square root of 1 minus cosine of x over 2. Cosine of x over 2 is 1 plus the cosine of x over 2 under the square root. And tangent of x over 2 can either be 1 minus cosine of x over sine x, or sine of x over 1 plus cosine of x. Okay? All of these, you will notice that on the left side of our equations, it's an x over 2, so we're looking at half of whatever the angle x is. And on the right side, all of our functions are in terms of x, so these are the values that we're given. The other thing to notice is that some of these have a plus or minus in front of them. And when you're evaluating these functions, the plus or minus will depend on what quadrant your x over 2 lies in. Okay? So for example, if x is 140 degrees, then x over 2 is 70 degrees. And so I'm going to use the fact that 70 degrees is in quadrant 1, and my values are going to be positive. Okay? If my x was 300 degrees, then my x over 2 is going to be 150 degrees, which means I'm going to be in quadrant 2. So my sine would be negative, but my cosine would be positive. Okay? So you're just going to need to determine that. And notice there's no plus or minus on the tangent. Because we're using the cosine and the sine values, your tangent will come out positive or negative depending on what quadrant you're in. It'll kind of work out itself. So these are the 3 half-angle formulas you're going to need to know for some of your later problems. Again, both in this class and in your calculus course. Okay. So let's look at an example of some half-angle formulas. Let's find the sine of x over 2, cosine of x over 2, and tangent of x over 2, given that cosecant of x equals negative 3 halves, and x is in quadrant 3. So again, to start this, I want to start by setting up my triangles. And if you recall, all of my half-angle formulas involve a cosine of x. So when I set up my triangle, I also want to be able to find the cosine value and then use that to solve for the other things. So setting up my triangle in quadrant 3, we'll have that the opposite over the hypotenuse is negative 2 over 3. And using the Pythagorean theorem, we can get the other side as square root of 5. Again, we're going to make that negative since we are in quadrant 3. So our cosine of x is going to be negative root 5 over 3, and our sine of x is going to be negative 2/3. And now using that information, we can set up our sines and cosines and so forth. Again, one of the things to notice is for sine of x over 2 and cosine of x over 2, I need to know what quadrant x over 2 is in. So here, if we notice, x is in quadrant 3, which means it's going to be between 180 and 270 degrees. So if I divide out by 2, it tells me that x over 2 is going to be between 90 and 135 degrees, which is in quadrant 2. Okay? And again, that's needed because that tells me that my sine in quadrant 2 is positive, cosine is going to be negative, and tangent is going to be negative. So when we get our values, if those signs don't match up, then we know we did something wrong. So sine of x over 2 is going to be the positive square root of 1 minus a negative root 5 over 3, all divided by 2. Now, again, there's going to be a lot of simplifying in this problem. So first, we're going to get rid of the 3 in the denominator of the numerator. So get a common denominator, so 3 plus the root 5 over 6. And then we need to get rid of the root out of the denominator. So multiply top and bottom by root 6 to get root 18 plus 6 root 5 underneath the square root, all divided by 6. Okay, so there's our simplified expression. For these, you should give exact answers unless you're asked to round to a decimal place. We'll do the same thing for cosine. So for cosine of x over 2, we get the negative square root of 1 minus root 5 over 3 divided by 2. Notice here we have basically the same numbers, the difference is a couple of minus signs. So once we get a common denominator in the numerator and rationalize the denominator, we'll get the negative square root of 18 minus 6 root 5 all over 6. And lastly, for our tangent of x over 2, we're going to use 1 minus the cosine of x over sine of x. So we'll get 1 plus root 5 over 3 divided by negative 2/3, getting a common denominator on the top, and then dividing out, we get 3 plus square root of 5, all divided by negative 2. Okay, so we can use the half-angle formulas just like we used the double-angle formulas in evaluating and simplifying expressions. So, for example, let's evaluate tangent of 1/2 cosine inverse of 2/3. So here, again, just like with all of our other compositions, we're going to start by setting up our triangle. So cosine of theta will equal 2/3, and by our Pythagorean theorem, our opposite side is going to be square root of 5. From there, we know that tangent of 1/2 theta is going to be 1 minus cosine theta over sine theta. So tangent of 1/2 theta will equal 1 minus 2/3 over the root 5 over 3. Simplifying, we'll get 1 over the square root of 5. And then to rationalize tells us that tangent of 1/2 cosine inverse of 2/3 will equal root 5 over 5. Simplify the expression 1 minus cosine of 4 theta divided by sine of 4 theta. Now here again, we can see that this is set up a lot like our half angle formula for tangent. It's a 1 minus cosine over sine. So by our half angle formula, this tells us that we're looking at tangent of 4 theta divided by 2, or tangent of 2 theta. Now again, our half angle formulas can be used to evaluate actual expressions. So here, let's say we want to evaluate cosine of 112.5 degrees. Okay? Well, 112.5 is not one of our nice angle values, but we can see that if we use our half angle formula and treat that as x over 2, if we treat that as our x, then x over 2 means we're looking at a 225 degree angle that we cut in half. So by our half angle formula, cosine of 225 over 2 will put us in the second quadrant. So we're looking at, again, 112.5, which will be in the second quadrant. So it's going to be a negative square root of 1 plus cosine of 225 degrees divided by 2. From there we can simplify. 225 is one of our nice angles, so cosine of 225 is negative root 2 over 2, which we can simplify down to 1 minus root 2 over 2 over 2. Underneath our square root with a negative out front, we're going to get a common denominator in the numerator and then rationalize that denominator to get negative square root of 2 minus root 2 all divided by 2. Again, for these you should get exact values unless otherwise stated. So if you're just seeing evaluate an expression and it doesn't say to round, you should be trying to use exact formulas. So now let's evaluate the sine of pi over 12. So again, we can look at pi over 12 as being pi over 6 divided by 2. So we can use our half angle formula for sine to determine what the value is. Okay, pi over 6 divided by 2 is going to end up in the first quadrant, so pi over 12 is definitely less than pi over 2. So sine is going to be positive. And so using our formula, so we'll get the square root of 1 minus the cosine of pi over 6 divided by 2. And then evaluating our cosine and rationalizing the denominators, we'll get the square root of 2 minus root 3, all divided by 2. The last set of formulas that we're going to look at in this section are the product to sum and sum to product formulas. Again, these formulas will be useful in completing calculations and in solving identities, but they're not ones you need to memorize. And I'm going to just let you pause the video here and you can look at the different formulas. The first four are our product to sum formulas, meaning I'm starting with a product of sines and cosines and then changing them to sums and differences of angles. Okay, and then the last four listed there are our sum to product formulas, where we start with a sum of sines and cosines and end up with products of sines and cosines. Okay, these formulas are reversible. The ones on the first four are the exact reverse of the second four. It's just not as clear because they're written kind of differently. But these formulas do go together. And again, like I said, you don't have to memorize these. For this class, you will see these in the activities and in the assignments that you're asked to do. You will not be asked to use these on the exam without being given the formula. So one of the reasons these formulas are useful is in finding values of expressions. And sometimes the expressions may not have such nice angles, but if we use the sum to product or product to sum formulas, it makes the angle values much nicer. So for example, let's evaluate 2 sine of 52.5 degrees times the sine of 97.5 degrees. Well, if I look at this, this starts out as a product. And so if we use our product to sum formula, we can look at sums and differences of those angles, which may turn out to be nice angles. So looking at the product to sum for sine of an angle times the sine of an angle, we're looking at 1/2 cosine of u plus v minus cosine of u minus v. So in this case, we're going to let u be the 52.5, and v is going to be the sine of 97.5. So rewriting our expression, the 2 out front, we're just going to carry along. So it'll be 1/2 cosine of the sum of the angles minus cosine of the difference of the angles. And here, when we go ahead and calculate those sums and differences, we see that we get cosine of 150 degrees minus cosine of a negative 45 degrees. So here we are going to take into account a couple of our properties. The first is the cosine of negative 45 degrees is the same as cosine of 45 degrees. Remember, that's an even function. Cosine of 150 we know is going to be negative root 3 over 2, and the cosine of 45 is root 2 over 2. And since these can't be simplified much further, it's just going to be minus root 3 minus root 2 over 2. In the next example, we want to evaluate the cosine of pi over 12 plus the cosine of 5 pi over 12. Now again, both of these angles are not so nice. Pi over 12 we could use a half angle formula for. We've looked at that already. Cosine of 5 pi over 12 doesn't quite work as a half angle or a double angle. And so here we can notice we're looking at the sum of two cosines. So using our sum to product formula, we can say that cosine of x plus cosine of y is 2 times the cosine of x plus y over 2 times the cosine of x minus y over 2. So we're going to let x equal pi over 12 and y equal 5 pi over 12. So we're going to simplify these and then evaluate the expressions and then simplify the value. So we'll get 2 cosine of pi over 4 times cosine of negative pi over 6. Again, using our even properties, that's just going to be cosine of pi over 6. So 2 times the square root of 2 over 2 times the square root of 3 over 2, which will simplify down to root 6 over 2.